So good morning, everyone. Welcome back to Math 115. How are you all doing? Making it through? Okay, good. Before we talk about math today, I figured I would tell you all that I'm going to be giving a talk. So here's my special flyer. Well, I didn't make this flyer, but someone else made this flyer for me.
Oh, wow. You're so professional.
Thank you, yes. I usually show up to teach in like a t-shirt, but I am going to wear something nice to this talk. So I'm talking at the Gamecock Math Club. I don't know why I couldn't say that word. It just didn't come out quite right. Okay, so the Gamecock Math Club, and then Pi Mu Epsilon. Okay, so this is a talk I'm giving. So if you think that you might be interested in like higher level mathematical modeling, so maybe you're like an engineer and you think maybe one day I want to go to grad school or something, see what advanced math is about, then you can come and see this, and if not, then don't go. But I figured I would let you know that I'm going to be giving this talk. So if you think that's something interesting, it's going to be in Pettigrew, so that's right next to LeConte at 7 p.m. tonight. And I'm going to talk all about the research that I do on traffic flow. So we want to use mathematics to model traffic, and this is done in a really kind of interesting way through the theory of fluid dynamics, which is what I study. So if you want to learn about partial differential equations and the kind of very difficult math that we have to use in order to model fluids, that's what I'm going to be talking about.
Traffic flow.
Exactly, traffic flow.
But did you mean to use the word flavor?
Flavor? Oh, yeah.
Okay.
Yeah, well, like, you know, yeah, no, flavor. I don't want to give them a taste. I want to give them a flavor, and like, because I want it to be.
I feel like you should like.
I want it to be qualitative, as opposed to like, if I was going to give them a taste, then I would show like some actually like kind of hands-on thing. But for a flavor, I'm more like just going to kind of describe it.
All right.
So yeah, flavor seems way more apt to me. Okay. Thank you. Yes, thank you. I try. All right, so let's get back to our class. So today we're going to talk about section 4.1 and 4.2. You have 2 homework assignments which are due tomorrow, and 1 homework assignment which is due on Friday. Your next quiz is going to be this coming Thursday, which means that today we will have the review session in my office hours, which will be not in LeConte 439. They'll be in the other room, 109. So that's where we'll have our office hours. I will record the session and post it onto my YouTube channel as well if you want to study using that. Any administrative questions before we jump back in to chapter 4? I feel like nobody ever has any administrative questions. That's good. I guess I'm doing a good job. Okay. All right, so then let me remind you what we talked about last time. So last time we introduced chapter 4, and we started with the simplest possible thing, which is angles. And we had a lot of different words which we used to describe angles. I'll go through some of them now. The initial side was the side that we start on. The terminal side is the side that we end on. If we measure in a counterclockwise fashion, then we call the angle measurement positive. And if we measure in a clockwise fashion, then we call the angle negative in measure. So angles are coterminal anytime that they start and end on the same sides, is what I should say, on the same sides. Okay, so they need to start on the same initial side and end on the same terminal side. How they get there, how many times they go around, doesn't matter, as long as they start at the same spot and end at the same spot. Standard position is the name we use for when we put an angle in the coordinate plane. If we put an angle in the coordinate plane, then we always put the initial side on the positive x-axis, and that's what we call an angle in standard position. Regarding degrees and radians, so degrees is what the Babylonians came up with for measuring how different 2 directions are, okay? And they said, well, The most different they could possibly be is 180 degrees, and the least possible difference they could be is 0 degrees or 360, however you want to say it. These two things mean the same thing, and essentially it is 1/360th of a full revolution. So 1 degree looks something like this, maybe. Okay, that's like 1 degree. We do 360 of them, we go all the way around the circle. Okay, if your angle is less than 90 degrees, you call it acute. Greater than 90, it's obtuse. If it's equal to 90, then we call it right, and we use this special notation when we draw it. Okay, so radians are the smarter way of coming up with a way to measure angles, and we'd say, well, I can call this angle any number that I want. What's really important is that the ratio of this angle to, say, an angle which is twice its measure, then we should make sure that the angle which has twice its measure should have 2 times as many radians, right? This is what is necessary. And then we need to know how many radians go all the way around. And if we know those 3 things, we'll be able to have a system. So we say, well, why not just say, if I take the unit circle here, if I inscribe, so inscribe means basically to draw inside of. If I draw this angle inside of the unit circle, then you can see that it will be like a slice of pizza, and that slice of pizza will have a crust, and that crust will have a length, and that length is what we call the measurement of this angle, okay? So if, by the way, your circle is not a unit circle, but like isn't great, but if it's a larger circle, okay, then of course the corresponding pizza crust is going to be significantly longer, right? So this only works when we use the unit circle. You're going to notice the unit circle is going to be emphasized over and over again for this chapter. So we also have, the circumference of a unit circle is 2 pi because we do 2 pi times r. The radius is 1, so it's 2 pi. So that is how many radians it takes to go all the way around, because that's how many inches or feet or units or whatever it takes to walk around the perimeter. Okay, so 2 pi radians goes all the way around. Pi radians is halfway around. Pi over 2 is just this right angle here, okay? And so then we learned how to convert back and forth between degrees and radians. Most of the time in our class, I will ask you to convert from degrees to radians, okay? But you'll need to know how to do both. I mean, if you know how to do one, you kind of know how to do both, because you just need to flip this fraction, right? So 1 degree is pi over 180 radians. 1 radian is 180 degrees divided by pi. Okay, so 1 radian is something like, what would we get if we divided 180 by 3.14? It'd be something like between 50 and 60 degrees, right? Because 60 degrees would be what we get if we divide 180 by 3. We're dividing by pi, which is a little bit more than 3, so it's going to be somewhere in the middle of these two. Okay, so that's what 1 radian is. Yes. So we talked a little bit more about coterminal angles. We said, well, I can find a coterminal angle to theta 1. If I have some angle theta, all I have to do to find a coterminal angle is do what? I add any multiple of 2 pi. So I could add 0 pi, I could add 2 pi, add 4 pi, add 6 pi, add negative 1 million pi. Okay, as long as it's an even number of pi's, then we add them to the angle, we get something which is coterminal. Why is that true? Because 2 pi goes all the way around the circle. So if I go a little bit, and then I go all the way around the circle, I'll end up back there again. If I go all the way around the circle once more, I'll end up back there again, and so on and so forth. So that's coterminal angles. Or if you want to do it with degrees, you need to add 360 degrees, right? So 720 is the same as a 360 in terms of where I end up looking at. Okay, and that's where we stopped. So, are there any questions on what we've covered so far for angles? All right, it doesn't seem like there are, so I'm going to move on and talk about, well, we're going to do 2 more things here. We're going to do a group activity in a second. But one more thing that I didn't quite get to yesterday was regarding complementary and supplementary angles, okay? So this is what we call two angles that sum to either 90 degrees or sum to 180 degrees, okay? So for example, if I wanted to find an angle beta, which is complementary to 73 degrees, what I need to do is I need 73 degrees plus the angle measurement of beta to be equal to 90, right? That's what I need. Well, I don't know why I'm writing it with that. 73 degrees plus the angle measurement of beta. Ooh, that's not a good beta. That's not great either. There we go, that's a little better. Is equal to 90 degrees. So if I want this to be true, I just need to figure out what beta is by subtracting 73 from each side. So I get beta should be what, 17? 17 degrees. Okay, and if alpha is supplementary to 73 degrees, have I made a mistake? Or you're just making fun of my handwriting? Okay, that's fine. Yeah, I'm well aware my handwriting's not too good. So if you're ever confused by something that I write, just ask. All right, so if alpha is supplementary to 73 degrees, then we want 73 degrees plus the angle measurement alpha to be equal to 180. So by the way, here's a drawing of the complementary angles. So we have 73 degrees is like here, so this is 73 degrees, and then this angle, oops, not that angle, then this angle here is what beta should be, right? It's the 17 degrees left that I need in order to get this right angle here, right? So for alpha, at this time, I need 17 degrees plus an additional 90, right? So 180 minus 73, we get 90 plus 17, which is 107, right? Degrees. So the picture for that one looks like, okay, here is your 73 degree angle, okay? And then the rest of the way is this 107 degree angle, which is of course an obtuse angle. It has to be obtuse because I'm adding it to an acute angle and I'm getting 180, right? That means whatever this number is definitely has to be more than 90, right? Okay. So this is supplementary and complementary angles. I expect that that's kind of familiar to you. Any questions on that? Okay, then let's talk about one more thing, which is arc length, okay? Arc length. So, the thing is, we actually defined, okay, radians to be the corresponding arc length on the unit circle. So, now we're going to ask the opposite question. We're going to say, well, if I put an angle inside which has alpha radians, then how long is this segment going to be? Well, it should be alpha, right? As long as we're on the unit circle. But we need to be a little bit careful. If we're on a circle of a larger radius, it's not just going to be alpha. It's going to be alpha times whatever the radius is of the circle, okay? All right, it's going to be alpha times whatever the radius of the circle is. Okay, so let's see how that works. So okay, so this time I use the letter theta. Theta, alpha, beta, all these letters usually represent angles. So if theta is an angle measured in radians, then the arc length of the part of the circle corresponding Hang on. We got to move that. There we go. So let's put alpha inside. Or theta, excuse me. Here's theta in standard position, always in standard position. Then what do we want to know? We want to know what is this length here, right? This length. Okay, so what I need in order to do that is I need to know what is the radius, right? Because if this is a much bigger circle, right, then the corresponding length you can see is much longer, right? This length here is much longer than the length shown in white. So the arc length is going to depend on two things, the inscribed angle and the radius, right? The inscribed angle and the radius. As long as our angle is measured in radians, we just take that angle and multiply with the radius. That's it. Just take that angle and multiply with the radius. Are there any questions on that? Okay, then let's go into a partner practice. I love this problem from our homework. This just really tickled me. So I'll read it out. A slice of pizza whose edges form a 25-degree angle with an outer crust edge 6 inches long was found in a gym locker. I don't know why it was found in a gym locker. Whoever did that should be in prison, but the FBI is investigating and they want to know what was the diameter of the original pizza so that they can, I don't know, bring whoever is responsible to justice, I assume. So what do we want to do? We have a slice of pizza with an angle. That's going to be a part of a circle, right? A part of a circle. So we want to know if the outer crust is 6 inches long. Okay. So that's going to be this measurement, right? Then what is the diameter of the original pizza? Okay. And if you finish that, you can try this extra problem as well. Okay, so I'm going to walk around and help you, but go ahead and get started on this with a partner. And if you don't have a partner, just scoot over until you have a partner. Veronica, do you want to work with Maya? And then Ashley, you can work with Alexa. Can you all read this well enough? Well, I've got a whole lot more space on the whiteboard, you know, to make giant letters. Right. So is the 25-degree angle inside? The arc length, right? It says this is going to be so the arc length is here. That's good. Okay. The radius is here. That's also good. So what else do we have? This equation is going to be true as long as our angle is measured in degrees. But what is our angle right now? Degrees. So we gotta convert, right? You remember how to do that? Or you got it somewhere? I mean, the way you can think about it is loosely speaking, if you have an angle measured in radians versus degrees, radians is going to be much smaller, right? So if you multiply by 180 over pi, is this number going to get bigger?
Oh, yes.
It would get bigger, right? So do we want the degrees to get bigger? No, we want it to get bigger, right? So probably multiply
One degree.
I have no idea.
Yes. Radius, if you have a piece of that, it's easier to do. That's this. How am I gonna figure out what You do? I'm the forever DS. Oh, you're the forever. That is exactly what it is. Then you have your picture. You're unwilling to see.
Let's see, the last time I played,
Yeah.
although they don't have as many, like, it's really just about, like,
Honestly, the like, it's a circle.
yeah.
That one's like, you're like,
It was, the whole game was over.
when you're there, you're like, okay, we're on kill.
Yeah.
Don't even try.
Like I have friends that are literally like there's
I'm currently in a campaign. And like, and it's, and basically,
Yeah.
because by the way, we don't have to like draconic local sorcerer. And I'm literally just here and point it.
Yeah. Yeah, exactly.
And then like someone else is like half dragon.
No, I just so hurt.
Someone else is half wizard. Like after you get like the really spell, magic items, but it's different kind of.
Yeah.
Going.
Alright, I gotta get back around. We'll talk more about this. Well, this looks pretty good. I prefer if you would have dropped.
I like a full, I like a full.
And I think you can
I'm gonna wear that.
Yeah, like that. And we have this equation here, right, which relates the radius, the arc length, and the inner angles, right? But it says, well, this formula only works if our angle is measured in radians, right? And what's our angle measured in? Degrees. So the first step is probably degrees.
I'm gonna need to find
So how we convert?
We're all.
We're gonna
usually
use-
I play with my.
Just like you said.
Okay, we're gonna use
All kind of picking on.
this one, right? So, you know, well, actually not this one, right? This is one radius. One degree.
I'm probably gonna try and.
I think that's here.
Because I've heard some.
Okay, so one degree.
Okay, 72.
So what if I have 25 degrees?
What do you worry about that?
We're gonna say 25.
There are categories.
But one degree is so we multiply 25 times pi over 180, then we'll have our measurement in radians. Once we have it in radians, then we know that what's going to be true. We know this is 6, right? So we're going to have 6 is equal to,
Like some of them are
whatever our answer is, right? Can be some fraction.
I know some.
I know I need to put
Right? So we have an equation like that. We're going to know this number and this number, and we'll be able to figure out what the radius is, right? If I know what the radius of the circle is, how am I going to figure out what the diameter is? Just multiply by 6. Does that help?
I
Yeah.
don't.
So what you want to do really is take the number of degrees you have, which in this case 25, and multiply by 6.
They do
Well,
exist. They do exist.
Okay, this is a little confusing how it's written. What you should say is maybe just convert to degrees, from degrees to radians, you multiply the number of times pi over 180. Okay, take out how many degrees you have, multiply by pi over 180. The radian is the opposite. You take however many radians you have, and you multiply by 180. Everything's in the front here.
Message me if you want to.
Okay, are y'all finished? Okay. Okay, are we?
What is the
Are you going? Okay, I think this is kind of where we want to go, right? We want to have this equation which is relating the angle, the radius, and the arc length, right? And what's the one caveat to the arc length formula? It says if what? If theta is measured in radians, then this formula will be true, right? So what we need to put here is not 25 degrees, but whatever 25 degrees is in
I had
radians,
this one.
right? So how do we get to radians?
The whole thing.
When
he
Right, well, we're gonna use the formula.
Where
It said 1 degree is pi over
He would
160
use
radians.
any
So if I have 25 of them, I just
It
do
was
25.
supposed to level up. Eventually.
So this is gonna be 25 pi
There's supposed to be like.
over 180 times
Even
radians
again.
is equal
And I was
to
playing with
6.
fire.
Yes. Once we've got that, we've got number times value. How's that gonna help?
So, and it's supposed to
The question says, what is the
So,
diameter?
when I got to.
Take radius
I
of 2.
was also playing the chance.
So we got here. So, like.
No, this was supposed to be. 80 days. So it was also.
Okay. You know what? We have this guy.
We never tried one shot. And either. Not the main boss. I did like 160 damage.
If I have radius
And
I was like out there walking around,
No, I
and I saw the flag and got
All of it.
he gave me a copy.
This
oh no,
one.
you said
Over 5 is the same as over 1.
Oh, I do have it.
fake too. And so and it had another
Is that?
see like
I know.
it's just
You got 4 and you already.
But I lost all the credentials and
like
I
I
went
wait
to the
which
So it means everyone's math
in my defense, he said I want to be strong.
He's a
And
respect.
find
He graduated from LSU. Like,
Yeah, it's just
and
how is that?
himself said no one can believe her.
Oh, yeah, you said that if you take her
It would probably fix that.
that was good.
And they have a
Because it was like so
Okay, let's come back together as a group. All right, I saw a lot of good work out there, so let me write down some of the things that I saw. So, one thing that I really like that almost everybody did was draw a picture. You should draw a picture. And I prefer the picture to exist in the coordinate plane, and I prefer that your picture incorporate a unit circle, or not a unit circle, but a circle in this case, okay? So here's our picture, and what am I going to do? I'm going to draw in my slice of pizza, which in this case is going to look something like this, okay? I prefer that, okay, you could draw the slice of pizza anywhere, right? Like I could draw it here, and here's my slice of pizza, but I think it's good to get in the habit of drawing angles in standard position. So what I'm going to do is instead of drawing it like that, I'm going to draw it where one side of my angle is on the positive x-axis. This is where I like to draw angles. And then, where's my crust gonna be? Let's use an appropriate color for the crust. Here's my crust. Okay, so what do we know? We know that this inner angle is 25 degrees and this length here is 6 inches, right? 6 inches, okay. So, what I want to find out is what is the diameter, right? What is the diameter? Well, I don't have any tools that will help me find the diameter, but I do have a tool which we just learned which will help me find the radius. And the radius is half of the diameter, so if I just multiply it by 2, I'll get the diameter. So we're gonna go for the radius. But what was the hang up? Why can I not just go ahead and apply this formula? Yeah. This formula is only true, it literally says if. There's a big if, right, before we say the formula. And the if says if theta is measured in radians, then this is true. Otherwise, it may not be true. In fact, it will not be true if we're measuring in degrees, right? So our angle is measured in degrees. So we have to convert, right? So how do we convert, okay? I feel like I may have not communicated this in the best way possible last time. What I said was 1 degree is equal to this many radians, and 1 radian is equal to this many degrees. Well, if 1 degree is equal to this many radians, if I have 25 degrees, what should I do? Well, 25 degrees will be 25 times as many radians. So to convert, so from degrees to radians, what you should do is take however many degrees you have and multiply by pi over 180. To go from radians to degrees, you should take however many radians you have and multiply with 180 over pi. Okay? this is what we need to do. So we're going to use this method since we're going from degrees to radians. We're going to take 25 and we're going to put it in here because that's the number of degrees I have. So we get theta is 25 degrees, which is the same as 25 times pi over 180 radians. Okay? So if you want to simplify that, that's, what is it? It's 5 over 36. 5 pi over 36 radians. Okay, so this is how many radians we have. So we're just going to use the formula. It says the arc length S, that's 6 inches, is equal to the radius, which is still unknown. That's what we want to find out, times times 5 pi over 180, yes? No, 5 pi over 36. 5 pi over 36. So if we want to get r by itself, okay, I don't want anyone to be scared by this fraction. It's just a number, okay? You can type it in on your calculator and get a number. So this is a number equals r times a number. How do we get r by itself? We divide both sides by 5 pi over 36. So if I divide by 5 pi over 36, that's of course the same as multiplying by the reciprocal, which would be 36 over 5 pi. So we get the radius should be 216, which is 6 times 36, divided by 5 pi. So I'm done, right? I got the answer, right? Now, one step left to do. What's the final step? Multiply by 2, right? Because this is the radius. They asked me what is the diameter. So the original pizza diameter would be 400, would be D is 2r, which is 432 over 5 pi, which, let's see what we get when we do that. Did anybody figure it out in decimals?
27, I think.
That seems really big. Do I not even have pi on my calculator? Even in sideways mode? How could this be?
It's at the bottom, I think.
Oh yeah, it is. Thanks. Okay. 432 divided by parentheses 5 pi. Yeah, I'm getting 27.5. Is that what you got?
The number I got. I had 27.3.
That's so strange. 432 divided by 5 pi. All right, well anyways, I'm getting 27.5 inches. Okay? So that's a big pizza. That seems like really big, actually. 27.5-inch pizza. Okay.
That's a pizza that's like...
It's like a yardstick. It's almost a yardstick in diameter.
What's the book of the things that are like biggest? Well, like pizza.
25 degrees.
Let me answer that in a sec. Gavin, what's your question? Yeah, exactly. On a test, I would just tell you to stop here, right? Because you're not gonna have a calculator. Yeah.
I figured you let me use my P calculator.
Alexa, did you have a question? Same. Okay, different question. Are there any other questions on this one?
Academic genius.
All right, this is one of your homework questions, by the way, so you just got it for free.
How do you know the same number?
Sorry?
How do you know the same number?
Well, it won't be the same numbers. It'll be different numbers, but I don't want you to go and put in 27.5. I want you to go and use the same process that we just did. Okay, let's move on to something new. So next we're going to talk about the big one, okay? It's trigonometric functions. So we're going to define the 6 trigonometric functions presently. But before we do that, Before we do that, we are going to review a couple of things. So first of all, what I want to review is the unit circle. So what I don't want is for anyone to feel like we're learning something completely new. We already learned about circles, right? We learned the form of a circle is like, x minus h squared plus y minus k squared, right? Oops, should we go here? And then equals r squared, right? That's the equation of a circle, right? So if you can remember that far back, this was the formula that we used for a circle whose center is at h comma k and whose radius is r, right? So if we have a unit circle, that is to say what? Well, the unit circle is defined to be the circle whose center is 0, 0, and whose radius is 1. So if we put in 0 for h, 0 for k, and 1 for r, we obtain the equation x squared plus y squared is equal to 1. Okay, x squared plus y squared is equal to 1. You can compare this with the Pythagorean theorem. Why? Because if I am to draw a circle in here, then what? All of the points x comma y, which are on this unit circle, will satisfy the Pythagorean theorem for a triangle like shown. Right? This will be a right angle, and what is y? Y is this length, and x is this length, and 1 is this length. Why is 1 the length of the hypotenuse for every single triangle that I draw like this? Why is the hypotenuse always 1? Because it is the radius, okay? 1 is the radius. That tells us that the length from the center of the circle to the outside on a direct path is 1. So this is where we get x squared plus y squared equals to 1. It's the Pythagorean theorem. Okay, it's just the Pythagorean theorem. All right, so what is the radius of the unit circle? Of course, 1. How about the circumference? That's the length all the way around. What's the length all the way around? 360 degrees, or we should describe it in terms of, not in degrees, but rather in terms of units of length, right? So yeah, it's going to be 2 pi. So the radius of a circle is 2 pi r, or not radius. The circumference is 2 pi r, or pi d, right? And that's just equal to 2 pi times 1, which in this case is 2 pi. So you can identify this number in 2 different ways. You can say, well, the circle has the circumference 2 pi, but this is a measurement of length, which can be identified also with the number of radians which I must inscribe on the inside in order to go all the way around. So these 2 things there's a subtle difference between describing a measurement which is a length and a measurement which is an angle. When it comes to radians, you get the same number, but different units, okay? When I'm talking about the angle, I say 2 pi radians. When I talk about the circumference, I say 2 pi units. Or if we're in inches, I'd say 2 pi inches or 2 pi feet or whatever, right? 2 pi football fields or something like that. Okay, so how about the area? What do I get for the area of the unit circle? Anyone remember the formula for the area of a circle? Pi r squared. Pi times r squared, which is going to be pi times 1, which is pi. All right, and this is the graph, right? The graph is the collection of points, which are 1 unit away in distance from the center of the circle, okay? That is what a circle is. It's the collection of all points which are equidistant from the center. Okay, so I just pick a direction, I walk 1 mile away, and I get to one of the points on my circle. If I had picked a different direction, I'd get to a different point, or a different point, or a different point, right? All right, so that's the unit circle. Any questions about the unit circle? Okay, so the one thing that I want you all to always remember about the unit circle that I find when students do trigonometry they often forget is that the radius of the unit circle is 1, okay? So oftentimes I will have students who will draw a picture like this and they'll get to this point and then they're like, well, I don't know how to figure out what x and y should be, right? They don't know, how do I figure out what x and y should be? And the crucial piece of information that they're almost always missing is that they forget that you have this piece of information for free because we are in the unit circle. The radius, anytime I draw a line segment which goes from the center of the circle to the edge of the circle, it has to have length 1 if we're in the unit circle. Okay, so now what I want to review is something called special right triangles. Okay, so special right triangles are triangles whose side lengths are related to each other by a special rule. Okay, so way back when maybe you took a geometry class, you learned that, well, the length of the side is going to depend on what the angle measurement is across from that side. Okay, this is what we learn in geometry. And there's all sorts of theorems which will tell you about what the side lengths should be. But for a 45-45-90 triangle, you might imagine that the side lengths which are opposed from each of these two angles, since the angles are the same, we might expect the side lengths which they oppose to be the same. And in fact, that is true. So the way I'm going to write this is with an x. I'm going to say, well, if this side length is x, could be 7, 5, 1 billion, could be any side length that you want, right? Well, whatever that side length is, this side length will be the same as that. So I write x again, because if this one's x, then this one has to be x as well. And how do I get the last side length? Well, you could use the Pythagorean theorem if you want. You'd get what? X squared plus x squared equals the thing that I want squared. So it would be 2x squared equals c squared. So take the square root on both sides. I get x times the square root of 2 is equal to c. So this side length will have length x times the square root of 2. So let's see, for an example, I could have this side length is 3. So what are the other side lengths? Well, this one has to be 3, and this one has to be 3 times the square root of 2. Make sense? So if I know any of the side lengths, I can figure out any of the other side lengths by this relationship, right? So what I need to do if I want to go from one side length to another is say, well, the first thing we know is that if I want to go from either of these two side lengths to the other, they're just the same. If I want to go from one of these side lengths to the hypotenuse, I multiply times the square root of 2. And if I want to go from the hypotenuse to one of the side lengths, what should I do? If I know this number and I want to know what x is, I divide by the square root of 2. Okay? So that's 45-45-90 triangles. There's a similar relation which follows for 30-60-90 triangles, which says that if the side length across from 30 is x units long, then the side length across from 60 will be x units times the square root of 3 long, and then the one that is across from the 90 will be 2x, twice as long as the angle, or as the side length across from the 30-degree angle. Okay, so I'm always looking at, okay, what is the angle and what is the side which is opposite that angle? Okay? So let's do this example real quick for the 30-60-90 triangle. So all we know is that this is a 90-degree angle and this is a 60-degree angle. And I'm supposed to find out what these two lengths are if this side length is 3. Well, do I know what this angle is here? Why must it be 30? Yes, the sum of interior angles, by interior I mean this one, and this one. They're on the inside of the sum of interior angles is 180 degrees. So 180 degrees minus 90 degrees minus 60 degrees is equal to 30 degrees, so this must go here. So this is a 30-degree angle. So what do I have? They don't tell me what the one across from 30 degrees is. If I knew what that one was, then this one would just be square root of 3 times that, and this one would be 2 times that. But they only tell me the 60-degree angle side. So how do I go from this side to this side? How do I know this side over here? Well, if I were to go in this direction, what would I do? I would multiply times the square root of 3. So what am I going to do when I go the other way? I'm going to divide by the square root of 3, right? So A is going to be what I get when I take 3 and divide by the square root of 3, which of course I would rationalize the denominator and get 3 root 3 over 3. Okay, you multiply the top and bottom by the square root of 3. These two cancel each other out and we get 3, and then on top we have 3 root 3. And then we can cancel the 3's and we just get root 3. That makes sense. That makes a whole lot of sense. Why? Because to go from this side to this side, I multiply times the square root of 3. If I take the square root of 3 and I multiply by the square root of 3, I get 3. All right, how about going from here to here? Well, I would need to divide by the square root of 3 and multiply by 2 or something like that. But what's easier, in my opinion, is we already figured out what A is. We already know the 30-degree angle side. We can go from this side to this side really easily by doing what? Multiply by 2. So B is just going to be 2 times whatever the side length is, which is across from the 30, which we just figured out. So we get 2 times the square root of 3. Okay, so this is special right triangles. 45, 45, 90 triangles and 30, 60, 90 triangles are going to henceforth be mostly taken for granted. So if you need some extra practice on these, I'll post something maybe to the Blackboard for you all to practice if you need to get more familiar with this, because this is going to be a sort of a foregone conclusion that we can solve 45, 45, 90 triangles and 30, 60, 90 triangles. Yes?
Isn't there like a 3, 4, like 5 triangles?
Yeah, there's one more triangle which we could talk about. It's not going to be relevant. Well, okay, it'll be relevant, but it's not going to be relevant for the unit circle. Why not? Because here's a triangle inside the unit circle whose side lengths are 3 and 4. It goes like this. It's too big. It doesn't fit inside the unit circle. You see what I mean? So that's why that's not going to be as relevant for doing this, but I digress. I shouldn't have drawn that. Now I need to fix this. There we go. Okay, so sure, let's talk about the Pythagorean theorem, and then we'll talk about Pythagorean triples. So the Pythagorean theorem just says if you have a right triangle, okay, then the short legs, okay, by which we mean the legs that aren't the hypotenuse, right? These angles, basically, they have to be smaller than 90 degrees, right? So A and B are definitely smaller than C, and in fact, they're related by the theorem, which says that A squared plus B squared, the sum of the squares of the short legs will be the square of the long leg, okay? All right. So, yeah, okay, so Pythagorean triples, since we mentioned them, are integers. So remember, that's the one with the z. Actually, naturals, sorry. Natural numbers, so that's n. So these are numbers like 1, 2, 3, ... Those are the natural numbers, which satisfy this equation. So the famous one is that 3 squared plus 4 squared equals 5 squared. So 3, 4, 5 is what we call a Pythagorean triple. Okay? A Pythagorean triple is a set of 3 integers, whole numbers, which satisfy this equation. There's 3, 4, 5. There's like, what's the other one? Like 5, 7, 13 or something like that. Is that right? No, it's 5, 12, 13, I think. 5, 12, 13? Because 144 plus 25 is 169. Right? Yeah. So 5, 12, 13. And of course, any multiple of this. So like 30, 40, 50 is also going to be a Pythagorean triple, right? For the same reason. All right, so those are Pythagorean triples. Any questions on special right triangles or the Pythagorean theorem?
Do we have quiz this week?
On Thursday, yeah. Yep, quiz on Thursday. Okay, so we're going to launch into one more partner practice for today. So the goal is simple. We want to find all points on the unit circle with height y equals 3 over 5. We're going to have this kind of vague task. Some of the tools which we have just learned will be relevant and some of them not so much. So our goal is to suss out which tools are going to be useful for this. I highly, highly recommend drawing a picture. All right, and I'll come around and help as necessary.
Yeah, that's what I said. That's the one that I use skip product instead.
What I'm talking about is, right? One point is here, one point is going to be this point, right? So we have 2 points. And what we want to do is just like smooth it down. What do we say about this triangle? It's a right triangle. That's one thing we can say. We can say even more than that. How about the height of it?
Yeah.
It's 3 versus 5.
Or use the plain metaphor.
So if I have a triangle, it's a right triangle, and I know 2 are the side lines.
I didn't get a piece of, if you're going over, you have to start using it, so I have this. So it's not like it's down in Canada, it's just like. Yeah. So you use challenges for everything. I didn't get, it's like you're going, so I don't like. Yeah. Yeah, so like,
Okay, so
and then it would be the same thing.
this is gonna be one, that's go, right? Okay, but of course, we have points here. Height is 3 fifths. We're not gonna have.
I just do one thing, I said that one of the other side of us, I'm assuming that's what it says.
So what are we trying to do? We have height here, we have this, but then we're trying to find this point, and then one other point, right? This one over here, all of that. Height. 3 fifths, right? So we just draw these triangles, and we know this side length is 1 and this side length is 3 fifths. So we can figure out the other side length. This, right? We're gonna put 16 over 25, we're gonna put that in for y squared.
Like I was just saying.
So we have an equation. Oh, so this will get
It's like a math for overnight.
Oh.
Is it saying like why, like why is it or like
Alright, so what do we have? We have circle, right? I like to do triangle, but I'm not so sure how this is going to go. What is true? This is where the first plane, right? So this point on the circle has coordinates x, 1, right? And we say that the height of the point is 3 fifths, which means that the y coordinate would be 3 fifths. So I'm not going to put y coordinate 3 fifths, right? So what does that tell us about this? This is the height of 3 fifths, right? Why is that 3 fifths? Because 1 would take us from here to here, yeah? So a little less than this, 3 fifths. Okay. So, how many points are going to be on the circle? So here's 1 point, all around the circle, right? So how many points are we going to have on the circle whose height is 3 fifths? All of the points on the circle? Well, this one has 3 fifths, but this point, its height is something else, right? Because it's not as tall as that one, yeah? Are there any other points on the circle who have the same height as this one? Yeah, on the left side, we're gonna have one over here, right, that also has the same height, so we're gonna draw another triangle like this, right? And now what is our goal? Our goal is to find all points. We already know the y value of these 2 points. Both of them have y value of 3 fifths. This will be something negative as 3 fifths, right? So what's left to do? Find out what x is, right? And we have a nice triangle written. Right? What is this? It's a right triangle. Do we know anything about the length of the sides of this triangle? Yeah, which one? Yeah, the hypotenuse is going to have length 1. I claim that you know one other side length 2. Though I know the side length is supposed to be 1 because I know this length, right? That's this length here, right? This length is 3 fifths. So what do I do? I have a triangle. The right triangle, this side length is 1 and this side length is 3 fifths. You know any formulas which relate the side lengths of the triangle so that I can figure out what this one is? Yeah, what is that? Well, do we know what these angles are? We don't know what this is, right? So we're rather either 36, 90, or 45, 45. What does it say? It says that the small leg, take them, this one's x, take x squared plus y squared should be equal to the hypotenuse, right? 1 squared, which y is 3 fifths, so we have x squared plus 3 fifths squared equals 1, right? And then what do we get? We get x squared plus 9 over say 5 equals 1. So we subtract on both sides. We get x squared equals 1 minus 9 over 25, which is 25 over 25 minus 9. So what do I do? I subtract the numbers. I get 14. So if I have the equation x squared equals 25,
They're not, how can I figure out what x is? I have. No, I have.
I think it's hard when you write it like this, right? It's hard to think of like, oh, I gotta think of a fraction. If I multiply fractions together, I get this number. It's too hard. Let's make it easier. The square root of a fraction is the same as the square root of the numerator divided by the square root of the denominator. Now it's a lot easier. Yeah, right? How about the top? Plus or minus. And on the bottom, plus or minus. So, the next coordinate here is what? How about this? What's the next coordinate here? It's negative. This looks good. You found one x value such that the height of this point is 3/5. But there's one thing left to do still, which is we're supposed to find all points on the unit circle with height 3/5. Are there any others? Is height is 3/5 other than this one? Maybe. Well, what is the height? This height here is the same as this height here, right? So here is 3/5. So the points on the circle are all of the points all the way around. Are there any other points? Height. Okay, this is from here to here, right? Is the same as this one. Yeah. Where would it be? Is this point, does this point have the same height as this one? No, it's gonna have height that is not 3/5, but it'll be like negative 3/5, right? How about another point whose height is positive 3/5? If I do this one, this is the same height as this. Imagine this is the floor, right? This is the floor, and then like this direction is up, right? So this point is 3/5 of the way off of the floor, right? And then so is this. So when we're talking about height, we're talking about distance to the next point, right? If these two points are the same height, this point has this is the x value, and this is the y value, right? So 4/5, 3/5. What about this point? All right, let's come back together as a group. How much time do I have? Not enough. All right, so we won't actually get to trig functions today, but we will see this example worked all the way out. So let's draw. The first thing we should draw is, well, they want us to have all the points on the unit circle. Let's draw a unit circle. That way we know what we're dealing with. Okay, so what do I mean when I mean points on the unit circle? What I'm referring to is all of these points, right? All of these points have an x and a y coordinate, okay? Have an x and a y coordinate. And those x and y coordinates satisfy the equation x squared plus y squared is equal to 1. And I want to find the ones such that the height is 3/5. So the y coordinate must be 3/5, okay? The y coordinate must be 3/5. Now, the y coordinate is the height, okay? So what do I mean by that? What I mean is this is the y-axis, yes? This is the y-axis, and this here is height 1, right? Because it's the unit circle, so this length is 1. So 3/5 would be somewhere like here. So I'm looking for points on the unit circle whose height is 3/5. There are exactly 2 of them. The first one is this point here. This point has height 3/5. This is the point x, 3/5. And then I have another point on the other side whose height is the same, and its x value will be the negative of whatever we have on the right-hand side. So to find out what x is, what must I do? I must, of course, draw a triangle. If I draw a triangle here, or a triangle here, regardless of which one we get, we have the formula x squared plus y squared is equal to, what's the radius? It's 1. The radius is 1, so 1 squared. So we get x squared plus 3/5 squared equals 1. Therefore, x squared equals 1 minus 16 over minus 9 over 25. And that's equal to 16 over 25. And there were several people who were able to then take the square root and say, well, okay, therefore x is equal to 4 over 5. All done, except not quite all done, are we? Because we missed one of the points, right? The other point is where x is equal to negative of that, right? We need to make sure when we take the square root, keep in mind there's going to be a negative square root. All right, so the final answer would be negative 4/5, 3/5, and 4/5, 3/5. All right, that's it for today.
Goodbye. Have a good day.
Yep, you too.